Hello, my name is Todd Thompson, and I'm a professor of astronomy at Ohio State University and a member of the Center for Cosmology and Astroparticle Physics. I'd like to thank the organizers for giving me the opportunity to talk to you today about interpreting X-ray observations of hot galactic winds. I'll be summarizing some of the work that Dustin Nguyen, a graduate student here, and I have been working on for the last year or two, summarized in this archive posting that just came out in the last couple weeks. First, I need to tell you about galactic winds. Galactic winds are massive outflows from galaxies that we observe at both low and high redshift. Easily observed winds are relatively rare in the local universe, but they're very common at high redshift, and they are because the galaxies are very intensely star forming. They have a lot of star formation per unit area. In this picture, you see the local galaxies, nearby galaxies M81 and M82. And from M82, you see this wind erupting from the disk. And that's going to be the subject of my talk today. So here's a zoom in on the famous M82 starburst. You see a stellar disk inclined to the line of sight. And then in the center, you see a burst of star formation where many massive stars are being produced. And producing feedback via their supernovae and their strong radiation fields that drives gas out along the minor axis of the galaxy. The M82 starburst has a star formation rate listed here of about 10 solar masses per year and a radius of just 250 parsecs. If you divide those numbers, you see that there are approximately 60 solar masses per year per kpc squared. 60 solar masses per year per kiloparsec squared. You can compare that to the Milky Way. The Milky Way is a passive galaxy, not forming very many stars, and is much bigger. It has about 1 solar mass per year of star formation and a radius of about 4 kiloparsecs, making it much, much larger than the M82 starburst. If you divide those numbers, you find 0.02 solar masses per year per kpc squared. And the ratio between those two numbers is 1,500. That is, in the M82 starburst, in the core of the starburst, there are so many massive stars forming that the rate of massive star formation is 1,500 times that of the Milky Way. And what that means is that you have an incredibly high density of supernovae, stellar winds, and other energy injection mechanisms that eject this matter along the wind axis. The winds that we see are multi-phase and multi-dynamical. We see gas being ejected from the disk in all phases. Here is a picture of M82 in the far ultraviolet, showing dust scattering of far ultraviolet photons, showing that there's dust in the wind. Here is the soft X-rays, showing X-rays being emitted up and along the what we call the minor wind axis. And here we see H alpha emission and nitrogen 2 emission from the same wind. The X-rays show us that there's this hot phase gas of 50 million degrees Kelvin. And the notion is that it's flying out at 1,500 kilometers per second, super fast velocities being ejected from the galaxy. In these optical lines in H alpha and in nitrogen 2, we can probe the dynamics of the gas, and we can see that it's actually flying out at around 600 kilometers per second. Those velocities are way in excess of the escape velocity from the galaxy, and so we expect this material to be ejected into the surrounding, what we call circumgalactic medium. We want to understand what the origin is of these fast and massive winds. And the reason we want to understand that is because the amount of gas that's being ejected is significant compared to the star formation rate. If we look at this plot over here from this collection by Heckman and Borthakur, the mass flux out in this wind, when looked at for many, many galaxies, is very large. So here is 10 and 100 solar masses per year being ejected from these galaxies, where the star formation rate is here. So for many different galaxies, we see many different star formation rates, ranging from near M82 star formation rate here at about 10 solar masses per year, up to galaxies at 100 to 1 and even smaller. And we see a correlation that galaxies that are more star forming are ejecting more mass. And why is that important? What we see is that for a star formation rate of around 10 solar masses per year, we see mass being ejected up to 30 solar masses per year. And what that means is that the fuel for star formation is being ejected. Galaxies are forming stars out of the gas within them, yet these winds are ejecting the gas out at a rate that's even larger than the star formation rate. And what that means is that the wind phenomenon, this ejection of gas from the galaxy, is actually helping to turn the galaxy off. It's helping to stop the galaxy from further star formation. So it's leading to the transformation of galaxies from star forming galaxies into passive galaxies that are no longer star forming. When we look at the velocities, we can measure the velocities using spectroscopy in some of the optical and UV absorption and emission lines. What we see is that as galaxies go to higher and higher and higher star formation rate per unit area, the velocity that we see becomes higher and higher. So for M82, the starburst that I mentioned at the beginning, the star formation rate per unit area was around 60 solar masses per year per kpc squared. And we see gas flying out of it in the optical and UV emission lines of approximately 600 kilometers per second. But even more massive and more intense star forming galaxies out here reach velocities of up to 2,000 kilometers per second. So what we find when we look at galaxies is that a small fraction of the gas that was an initial dark matter halo that collapsed to form a galaxy actually ends up in stars. Most people don't think about galaxies as doing anything, but galaxies are not just passively sitting there. What's happening is that gas in them and gas raining down on them is processed into stars. And what we find is if those stars are processed very rapidly in a starburst, in a burst of star formation in a small area, that matter is ejected and it turns off the star formation. So we'd like to understand why a small fraction of all the gas in a dark matter halo ends up in stars. We'd like to understand why a small fraction of all the metals produced by stars is retained. We find that when stars are formed and when stars evolve, they produce metals. Massive stars produce iron, magnesium, oxygen, silicon, and a small fraction of those metals are actually retained in the galaxy. The rest is blown out in these winds. We also see that there's a large reservoir of cool metal-rich gas in the medium around galaxies that presumably has been ejected. And the fundamental question we want to address is what mechanism accelerates gas out of galaxies, removes these metals, and enriches this circumgalactic medium, CGM, that I have here. A standard answer is that the supernovae inject energy. Supernovae go off, massive stars produce supernova explosions, and when they do, it heats the matter, and it produces a hot, super fast outflow that sweeps up cool clouds and drives them out via ram pressure. But recent X-ray analysis of observations of the hot gas of M82's wind raises new mysteries I wanted to tell you about. So here's an X-ray picture from Lopez et al. 2020 of the starburst M82. The galaxy is here. The starburst is down in this core. There's tons of hot gas being produced, presumably by many, many, many supernova explosions over many millions of years. And that produces a hot gas that then escapes along the wind axis, the minor axis to the south and to the north. What Lopez did was she divided this region up into different quadrants to the south and to the north of the starburst region. And in each one of these boxes, going from the starburst core out to the south and from the starburst core up to the north, she computed found the X-ray spectra. Here is a picture of those places, and here are the different quadrants to the south and the different quadrants to the north, and here is the disk region. And so what you see here is an X-ray spectrum that shows a very strong thermal component, and then emission lines from a number of different highly ionized atomic species, including magnesium, neon, calcium, silicon, and others. So in each of these boxes, Lopez et al. Were able to derive the temperature and the density and the composition. And it's this analysis that raises these important questions about the physics of the hot winds. So another plot from Lopez et al. here is the temperature profile as a function of distance from the starburst core in kiloparsecs. So here at 0 is the starburst core, and then to the south, 1 kiloparsec, 2 kiloparsecs, and 3 kiloparsecs. This is the temperature profile going from several by 10 to the 7 Kelvin, dropping very steeply, but then a flat profile here and a flat profile here. Similarly, the density can be derived along the wind axis. This, again, is the starburst core, and you see the density falling off here rather slowly compared to these models. There's a number of models that are fit to the central region and do a terrible job. They do not at all reproduce the temperature profile on kiloparsec scales, nor the density profile on kiloparsec scales. And that's really the mystery that I wanted to talk to you about. I want to tell you about how these models are produced and why they fail, and how we can fix those models to make them more in line with these new X-ray observations. In addition to deriving the temperature and density profiles that I'm showing you here, Lopez also derives abundance profiles. Here, oxygen, neon, magnesium, silicon, sulfur, and iron. And what you can see is that the central abundance, for example, of sulfur is very, very high. And then as you go to the south and to the north, it very rapidly drops to become lower. Similar with silicon, starts with a high abundance and then becomes lower in the outskirts of this wind fluid. Oxygen is mostly flat. Neon has this interesting uptick here. Magnesium mostly flat but decreasing, and iron mostly flat. So the mystery is, how in these observations do we explain this very flat temperature profile and flat density profile, and how might we also explain these very rapid decreases in abundances, or perhaps just the flat abundances? How do we put those into one consistent picture? And I'm not sure we have a complete picture of everything, but we have definitely made an important improvement. In order for me to tell you about that, I first have to tell you about what these models are and why they fail. So how do we usually interpret these X-ray data? What's usually done is, in the center of this starburst region where all of these supernovae are exploding, we say there's some region of radius r, that has energy and mass, E dot and M dot, being injected into it. We then postulate that that hot fluid is produced by all this energy injection. So we imagine that supernovae are going off again and again and again. And every time they do, they dump in a certain amount of energy. That's the energy of a supernova, which is some huge number, 10 to the 51 ergs. We further postulate that in this region, a certain amount of mass is being injected. We parameterize the energy injected as the energy of the supernova, all the supernovae going off in that region, with this parameter alpha. And we also parameterize the mass loss rate as being proportional to the star formation rate. I told you that in the center of M82, the star formation rate is about 10 solar masses per year. And so we can make different models that have a certain amount of mass injected and a certain amount of energy injected. And if we do that, if we put energy and mass into a volume, we derive some properties. This was done by Chevalier and Clegg in 1985 and by others. What you do, if you have a typical amount, if supernovae are going off at a certain rate, and you're putting in a certain amount of mass, you derive a temperature on the scale of R, the region where you're putting this energy and mass in, of approximately 10 to the 7 Kelvin times alpha, this efficiency factor, divided by beta, this mass loading factor. Similarly, you expect a hot gas velocity, because this stuff is superheated, it should expand, of 1,000 kilometers per second times alpha divided by beta to the 1/2. And observations of the core indicate, observations of Lopez and others, particularly Strickland and Heckman, show that in order to match the X-ray observations in the core, you need alpha to be about 1. You need approximately all of the energy from supernovae to go into the hot fluid. And you need a mass loading factor of about 0.2 to 0.4. Now for radial scale bigger than the region that we're putting in, we just expect a material to expand. A superheated material that's expanding into space freely will have a constant velocity. It will have a density profile that's 1 over r squared. That is, as the radius increases, the density should drop as 1 over r squared. And the temperature, because it's expanding adiabatically, should expand with another power law, r to the minus 4/3. And these models are shown here for different values of the radius. And what you can see is that they do a terrible job. They do not fit the temperature profile, this flat temperature profile, and they do not fit the density profile. And the question we asked is, what could flatten these density and temperature profiles along the wind axis. What physics is this very simple spherical model missing? And there are a couple of things you might think of. And those are the things I want to tell you about. The first one is, what if the wind is not spherical? The wind actually, the X-ray profile does not actually appear to be spherical. It appears to be somewhat collimated. The X-ray profile, the X-ray surface brightness profile looks much more cylindrical than spherical. And flow through a pipe, a tube, like this cartoon that I've drawn here, is very different than spherical expansion. And it's controlled by this function, this areal function we call A of S. So along the wind axis S, the area is changing. Exactly how it's changing, we can derive from the X-ray surface brightness profiles. But if flow in a pipe is different from spherical flow, and so what if the flow is non-spherical? Why don't we modify this model, this hot wind model, to include an arbitrary areal shape that we can track? That's the first thing. Now, the second thing that we can do is we can imagine that cold material, clouds of cold gas, are being injected into the hot wind as the hot wind expands. So imagine this very superheated hot wind, heated by all these supernovae in this inner region, and it begins to expand. And as it does, it sweeps up, let's say, small, cool clouds of gas. What happens is those on a microscopic scale, or a scale that's microscopic by astrophysical standards, let's say several parsecs in this case, the clouds are shocked. The cool cloud in a hot supersonic medium will be shocked, it'll be shredded, and it'll be incorporated into the hot flow. And what we call that here is a volumetric mass loading. We're basically saying the wind is moving through this pipe, which I've sketched here. And then as it's going through this pipe, we imagine small clouds, because the whole region is littered with small, cool clouds. Those clouds are shredded and shocked and incorporated into hot flow. And we ask ourselves, how would the bulk properties of the hot gas change if, one, the flow is moving through this arbitrary areal function A of S, and two, if it was being mass loaded by cool clouds? And we can write down the equations of radiative hydrodynamics when that happens. And the general equations are shown here on the left-hand side. So what we have here is we have steady flow in a pipe. And so this equation here expresses mass conservation through the area element A for a given density of material and velocity of material. So this controls the divergence of the flow. This equation is the momentum equation. It shows how the gas accelerates and decelerates. The velocity, this is the acceleration, the velocity along S increases if you have a negative pressure gradient. So a negative pressure gradient makes a positive acceleration. But the material can decelerate because of gravity. That's what grad phi here is, the gradient of the gravitational potential. The gravity can slow down the gas. And also, if you add mass, mu dot here, if you conserve mass and you have a volumetric mass loading, as I've illustrated here, if you add mass, this mu dot, this is grams per cubic centimeter per second being added to the hot flow, it slows down the hot flow because of momentum conservation. If you add mass to it, it has to slow down. Similarly, the energy equation has this complicated character, which I won't describe too much, but what's basically happening is the hot gas is thermalizing. These are the general expressions for a 1D mass-loaded flow with an arbitrary areal function. And what you can show is in the limit of high Mach number and using an adiabatic index for an ideal gas of 5/3, which we expect this flow to be, that you can derive how the velocity decreases, it decelerates. You can derive how the density changes if A suddenly changes or if you mass load, and so on. And so what we've done is some model predictions just to get just to orient ourselves. And so what you see here is a spherical flow in the black line. And then we've put in different fluted geometries. Here we don't have any mass loading, but we just have a very fluted geometry where the flow can either expand very rapidly or is constricted very rapidly. And so if you follow this density profile, so here's the density of the wind expanding, and this would be a spherical expansion. But here, if we make the flow constrict, if we put it through a fluted opening that's very constrictive, the density goes up here. Whereas if we have a flow that diverges faster than spherical, it decreases very fast. So you can see the density profile could either increase or decrease depending upon how quickly the area function is changing. Similarly, the temperature can either go up or go down. Similarly, the velocity can either go up or go down. And the same with the pressure, up or down, and the Mach number, down or up. Meanwhile, the entropy of the flow is constant, because what we're doing is we're just using a fluted geometry, and the entropy of the flow does not change in a fluted geometry. We can also do examples where we put in mass loading. So here again, the black is a spherical flow. It's a spherical flow with no mass loading. But then what happens if you add mass? If you add mass, the velocity, and you start adding mass here, the velocity decreases. If you add more mass, it decreases further. If you add more mass, it decreases further. And if you add more mass, it decreases even further than that. But here's the interesting part. As you add more and more mass, the density of the hot flow increases. So here's the spherical expectation, and here is the density profile, which you can see is much flatter than it was before. Similarly, the temperature profile, which used to decrease in this and is like this in a spherical calculation, instead becomes very flat. And that's what we were going for, because we see these very flat profiles in M82. I also provide Mach number, pressure, and entropy profile here. So how do we apply this to M82? Well, what we do is we go back to the X-ray observations and we look at the lateral surface brightness profile across the wind. And we use the surface brightness profile of the X-rays that are being produced to derive the this function, A of S, right here. And what's happening is that this is a spherical calculation. The gray dashed is a spherical calculation. And yet from the X-ray, as you go north and south, but the X-ray observations show that the area function is actually quite a bit different from spherical and quite a bit different from spherical. So we can derive the X-ray from the X-ray surface brightness profile. We can derive A of S, and then we can use different mass loading and see what kind of fit we get to the data from the Lopez et al. Work. And so this is what our best calculation to date. So what you have here are the temperature, density, and velocity profiles, and entropy profile and composition profiles and X-ray luminosity profiles. And in each case, the X's are the data. So this is the very flat temperature profile of Lopez here to the south and here to the north. And this is what you would expect with a spherical model, which I've told you does not fit at all. Similarly, the density profile here and here, this is what a spherical model would predict. Now, what we do in the blue is we turn on our area function that's derived from the X-ray observation. So just using that new area function, which we derive from the X-ray data, and not using any mass loading, you can see the gray turns into the blue profile here, which is a much better fit to the data. Now, we can't quite match the density on either side, and we can't quite match the temperature on either side, but just changing the geometry of the flow dramatically changes the profiles you would expect for the temperature and the density. It doesn't change the velocity very much. The spherical velocity profile predicts that it should go to over 1,500 kilometers per second to the north and to the south. When we add the geometry to the north and the south, we get slightly lower velocities, but nearly the same. Now what we do is we add mass loading. We add this mu dot term. Now all we say is that there are a bunch of small clouds. Those small clouds are being shocked. That material is being incorporated into the hot flow, and it changes the bulk flow of the hot gas because it changes the continuity equation, the momentum equation, and the energy equation. That changes the thermodynamics of the flow, like the example that I showed you, and it changes M82's wind too. So here what happens when we add orange is the non-spherical and mass loaded. What we get is an even flatter temperature profile that very well matches the temperature data, a better but still not quite perfect match to the density. We get much lower velocities here because the material is expanding, and then boom, we hit it with mass loading, and the velocity decreases to about 900 kilometers per second instead of 1,500 kilometers per second on the southern side. The entropy we do not well match. The entropy can go up or down depending on mass loading. We can get close. We get some decrease here, but we're not able to match all of this structure. That's still work for the future that we don't quite understand. In the abundances, I mentioned a very strong decrease in silicon. So silicon abundance is shown here. We're saying it goes from, we normalize it, so it goes from 1, and then it drops very steeply, as I showed you from the Lopez et al. Paper. What we do is we say, well, we're mixing with this matter that we're mixing up, this cool gas, and we pretend, as a first guess, that that matter that's being swept up has very low silicon abundance. So if the material on the inside, the hot wind, is being ejected with a large silicon abundance, but then it mixes up material with very cold silicon abundance, then you would expect to see the silicon abundance decrease. And this is what the orange model is what we predict. If we mass load the medium this much and this much to produce these better density and temperature profiles, then we predict a decrease in the silicon abundance that's this big. Now, what's interesting, of course, is that the iron abundance doesn't do that at all. The iron abundance has this wiggly shape, which we're not able to reproduce. And so if the medium that was being swept up was very poor in silicon, then you expect this decrease in silicon. But if it was rich in iron, then you would not expect a decrease, because you would be mixing an iron-rich medium with an iron-rich medium to make the same net abundance. So we're not sure about that. If interpreted in this way, then you would say that this medium that has been swept up, these cool clouds that I keep talking about, are silicon poor and sulfur poor, but iron rich. Remains to be investigated. Another thing I want you to notice is that the actual X-ray brightness we can calculate. And again, the spherical model would predict a very steep gradient in the X-ray surface brightness because of this very steep drop in the density. Instead, when we put in our non-spherical areal divergence, we get instead this blue curve. And when we add the mass loading, we get numbers that are much closer to the observations, especially to the south. So my conclusions in summary are that galactic winds are important. They're important because they eject the gas from galaxies, which is the fuel for star formation. And so this affects how galaxies evolve. The hot gas, the superheated X-ray emitting gas that we see, may be crucial for accelerating gas out of galaxies, but X-ray observations refute these flatter temperature and density gradients than expected, and very strong abundance gradients from the X-ray spectroscopy that are difficult to interpret. Two physical effects we've highlighted that are probably important to interpreting these profiles are: one, this non-spherical areal divergence, that the flow is more cylindrical and less spherical. Two, mass loading of the hot phase. In this picture, cool clouds are destroyed on small scales and incorporated in the hot flow. Both effects change the bulk dynamics and thermodynamics of the hot flow. The mass loading affects the entropy gradient, the abundance gradients, the temperature and density gradients. So the results from our work indicate that you have to add 10 solar masses per year of material. That amount has to be loaded into the hot flow in order to match the observations. That is, in order to go from the blue curve to the orange curve here and here, you need to add to your initial flow another 10 solar masses per year. Remember, the star formation rate of M82 is about 10 solar masses per year. So what we're saying is that you have to eject approximately 10 solar masses per year, and then you have to mass load it with these small clouds at a rate of about 10 solar masses per year in order to match these observations. And this increase in the mass loading decreases the velocity from about 15 or 1600 kilometers per second to less than 1000 kilometers per second to the south. That decrease has not been observed. We do not have X-ray observations that have sufficient spectral resolution to show, to distinguish between those velocities. But there's a new mission that's coming up called XRISM, XRISM, which is a new microcalorimeter X-ray space-based spectroscopy mission that's going to have excellent spectral resolution, in which we hope we'll be able to see this factor of 2 difference. So what you can think of is that this mass loading that's needed to go from here to here predicts a lower velocity. And so we have a prediction that the velocities for the hot gas seen by XRISM should be smaller than previously expected. Most people expect that velocity to be about 2000 kilometers per second, and instead we're saying it should be less than 1000 kilometers per second. So thank you very much for your attention. I appreciate having the opportunity to speak with you, and I hope you enjoyed it. Thank you very much again. And this work is all summarized in Nguyen and Thompson, which is submitted and pending review. Thank you again.